Good morning, everyone, and very warm welcome to all you attend this webinar. Before we move into modern trend, welcome to ABC Trainings. Today's webinar, uh, today's webinar on earthquake resistant building design. Earthquakes are natural disasters that we cannot prevent, but through proper engineering design, we can definitely reduce damage and save lives. Today's session will cover basics of earthquakes, structural behavior during earthquakes, design principles, structural systems like shear walls and bracings, Indian seismic codes, case studies, further trends in earthquake engineering. Let us begin by understanding uh, what an earthquake actually is. An earthquake is the sudden release of energy stored inside on inside the earth crust. Now, why does this happen? The the earth outer layers is divided into large places called technoplates. These plates are constantly moving, but very slowly, just a few centimeters. Just a few centimeters per year because of friction between these plates. They sometimes get stuck. When they are stuck, stress keeps build, buildings up over time. When accumulated stress become greater than the strength of rocks, the rocks suddenly break or slip along a fault line. This suddenly break realization a huge amount of stored energy. This release energy travels into form of seismic waves. When these waves reach the surface of the earth, they causes the ground to shake, and that shakes is what we express of as earthquake. Now why is now why is this shaking dangerous? Buildings are mainly designed to carry vertical loads like dead load, live load. But during an earthquake, the building experience horizontal force. These latter forces create bending stress and torsion in structural elements like beams and columns. If the structure is not designed properly, this can lead to crack, cracks in wall, columns failure, foundation damage, complete structural collapse. And when buildings collapse, it becomes a major threat to humans' life. In fact, it is important to understand that earthquakes themselves do not kill people, unsafe buildings do. That is why understanding earthquakes is the first steps towards design safer and stronger structures. Next is importance of earthquake and resistant design. Now that we understand why Why an earthquake is? Let us discuss why earthquake resistant design is so important. Earthquake, Earthquakes are natural events. We cannot stop them, but we can control how our buildings respond to them. That that is where earthquake resistant design become critical. Next, we put protect slides or protect slides and priority. The premier and most important object of earthquake resistant design is to protect homeowners during an earthquake. Building experience a strong horizontal safety. If a building is not designed properly, it may collapse suddenly. When a structural collapse, it leads to serious injuries and losses of life. Having design also like resistant building because not collapse immediately when the damage occurs and it provides sufficient time for occupants to execute safely. This concept is called as life safety design. In additional to protective lives, it also protects valuable prote- uh, property such as homes, office, hospitals, schools, and other public infrastructure. Loss of priority will result in huge economic impact. Therefore, safe designs reduce both human and financial losses. Remember this important statement. Earthquakes do not like kill people. Unsafe building. Next is reduce structural damage. Earthquake resistant design buildings are designed to withstand lateral forces. These structures are properly reinforced, carefully detailed, designed with ductility, provide with proper load path. Such building may develop cracks during strong shaking, but they are designed to avoid total collapse. Good seismic design ensure columns remain in strict. Beam column joints stay strong. Foundation remains stability. Ex- Excessive swell is controlled. This is significantly reduce repair cost, reconstruction cost, downtime of buildings. For example, hospitals and emergency buildings must remain functional even after an earthquake. Proper design ensure operational safety. Next is essential in seismic swings. Main regions in India and around the world fall under earthquake prone areas. India is divided into seismic zones 2, 3, 4, and 5. Zones Zone 4 and 5 are considered high risk zones. In these areas, earthquake resistance design is not optional, it is mandatory. Indian structure, Indian standards such as Indian IS 1893 for seismic load calculation and IS 13920 for ductile detailing must be strictly followed. Ignore seismic design in these zones increased the risk of collapse. Urbanization is increasing rapidly. High, high-rise buildings, flyovers, metro systems all must consider seismic safety. Therefore, earthquake resistance design is essentially for long-term safety, sustainability, and legal companies. Next is seismic zones in India. Now let's understand how earthquake risk is classified in India. India is a large country with ve- very geological conditions. Some regions are some regions are more earthquake prone than to ensure proper structural design. They 4 and zone 5. Each zone represents a different level of seismic risk. Zone 2 low risk zone. Zone 2 is condition, con- considered to lowest seismic risk. Zone zone in India expected ground shrinking is rated low. Earthquakes may occur, but damages potential is minimally, minimally compared to heavy ones. Basic earthquake zones design provision are still required, even though even though it is called a low risk. It is does it does not mean zero risk. Engineers must still follow seismic design guidelines. Next is zone number 3. Zone 3 mandatory risk zone. Zone 3 falls under mandatory risk zone. Mandatory intensity earthquake can occur. Still, structural damage is possible if force considered in design of design or highly high rank zone 2 cities follows under zone 3. There, therefore, careful structural design as necessary. Zone 4 high risk zone. Zone 4 is categorized as high seismic zone and it is zone. Strong earthquake are expected. High potential for structural damages. Structural companies with IS 1893 and IS 13920 is essential. Regions in zones 4 include parts of Delhi, Jammu and Kashmir, Himachal Pradesh, Bihar, Gujarat. In this zone, ductile detailing and proper structural configuration are extremely important. Next is zone 5, very high risk zone. Very strong earthquakes are expected. Maximum ground acceleration values are used in design. Only high engineered structures are performed safely. The region includes northeast India, parts of Uttarakhand, Andaman and Nicobar Islands, some Himalayan regions. In in Zone 5, absolutely mandatory poor construction can lead to collapse. Important important technique concept Next is basic structural behavior during earthquake. Now let's see. Under, Understand what actually happens to a building during an earthquake. When an earthquake occurs, the building, the ground shakes in a horizontal direction. This ground movement directly affects to foundation and the building. Unlike gravity loads and which act vertical downward, earthquake forces act horizontal. These horizontal forces are called lateral forces. Next, that point is structural experience lateral forces. Du- During an earthquake, the ground suddenly moves. The building foundation moves along with the ground, but the upper part of the building tries to remain in its original position due to interior. This is different movement creates internal forces in the structure. The phenomenon is explained by Newton's first law of motion. A body at rest tends to remain at rest because of the interior and lateral forces are generated throughout the building's height. The magnitude of the force depends on building mass, ground acceleration, height of structure. Heavier buildings explain heavier earthquakes of forces. That's why light structure performs better during earthquakes. Next is vibration causes stress and deformation. Earthquake shaking is not a single push. It is continuously vibration back and forth. This vibration causes bending in beams, shear in columns, and torsion in irregular buildings, cracks in walls, dip, displacement at top buildings. The building started swaying. This swaying procedure internal stresses structural members. Next point is need of ductile and flexible design. Now the important question is should building should buildings be very regard to restrict research earthquakes? The answer is no. A, com- a complete rigid structure will attract a very high seismic force and may fall suddenly. Instead, structure should be ductile, flexible, energy absorbing. Ductility means the ability of structure to undergo large deformation without sudden collapse. A ductility building may crack, bend, and deform, but it will not collapse suddenly. This provides time for excavation, warning before failures, reducing life loss. Flexible structure can absorb the display seismic energy. This is achieved by proper reinforced detailing, strong column, weak beam concept, closely spaced stirrups, following IS 13920 guidelines. In simple words, we design building not to remain perfectly unmanaged, but we remain standing after strong shaking. Next is type of structural failures. Let's discuss about the most important parts of earthquakes engineering types of structural failure. Understanding failures patterns us design safer buildings during during earthquakes. Buildings usually do not fail randomly. They fail in predictable ways if not designed properly. Let us discuss about most common failures on one by one. The first is soft story failure. This is one of the most dangerous and common types of failure. A soft store fail occurs when one floor, usually ground floor, has significantly less stiffness compared to the upper floors. Company common examples: ground floor used for parking. Upper floors have masonry walls. Ground floors has open space with only columns. During earthquakes, upper floors are steeped due to walls. Ground floor is ex- flexible and entire lateral ground level. Columns at ground floor experience excessive bending. Columns fail under whole buildings collapse. This called as soft story collapse. Main buildings collapse in huge earthquakes due to soft story effect. This point is column failure. Are mostly typical structural element. If a building fails, the building may still stand, but if a wall fails, the entire structure can collapse. Collapse will occur due to insufficient reinforcement, poor ductility, detailing, weak concrete, strong beam, weak column design. During earthquake, columns express bendings and axial load together. If not designed properly, the developed shear cracks, sudden rights failure may occur. Next point is failures. Foundation failures plays a very important role in seismic performance. During earthquake, foundation may fail due to soil liquefaction, uneven settlement, in, insufficient depth, poor soil wear capacity. Liquefaction occurs in sand soil when ground shaking increase poor pressure, soil loses strength, it behaves like liquid. This can cause tilting of buildings, sinking, complete overturning. The next point is poor connection failure. Poor connection failure, another very common reason for collapsing poor, poor connection. Beam and columns joints are critical points. If connections are weak, loads cannot transfer properly, joints crack, structural integrity is lost. Collapse visible. Common mistakes includes indicate, ensure, lens, poor welding in steel structure, improper lab slips, lack of configuration enforcement. And the next point is about principles of earthquake resistance design. Understand how buildings fail during earthquakes. Let us discuss about most important part of the principles of earthquake resistant design. These principles help us design that survey strong ground shaking. Let us discuss about them one by one. Lightweight structure. One of the fundamental principles of earthquake engineering is reducing building mass. Why? Because earthquake force depends on mass according to basic physics. Force is equals to mass into acceleration. This means heavy, heavier building higher seismic force, lighter building lower seismic force. So when we reduce the weight of structure, we directly reduce the earthquake force acting on it. How can we achieve this? Using lightweight construction materials, avoiding unnecessary heavy cladding, avoiding very thick slabs if not required. Use lightweight partitions instead of heavier masonry walls. However, lightweight does not mean weak. It means and insufficient design. Design efficient design. Sorry. Smart design always balance strength and weight. Next point is seismical symmetrical planning. Symmetrical planning plays a very important role in seismic performance. If a building is symmetrical in plan or seismic force are distributed evenly, irrigation shapes such as L, T, and U, L-shaped buildings can causes of torsion during earthquake. Torsion means twisting of the building. When the torsion occurs, one side of building ex- experience more stress. Even displacement occurs. Structural elements may fail out permanently. Therefore, rectangular or square buildings plan perform them during earthquake. Regular geometry better suitable. Next point is poor load. What? This is one of the most critical principles in structural design. Earthquake force must be travel safely from the top of the building down to the ground. This continuous path is called as load path. They include the idle loads, transfer sequences, roof to slab, slab to beam, beam to column, column to foundation, and foundation to soil. The next point is good quality materials. Good quality materials, even the best design will fail if construction material are poor. Material quality directly affect earthquake performance. For reinforced concrete structure, proper concrete mix ratio is essential. Adaptive curing must be done. Steel reinforcement must be concrete concrete grade. Proper placement and compact are necessary. Poor quality material may lead to brutal failure, cracking under small stresses. Next slide is about ductility in structures. If you remember only one concept of from today's session, if ductility saves lives. What is ductility? Ductility is the ability of material or structure to undergo large deformation before failure without sudden collapse. In simple words, ductility structure bends and bends and deforms before breaking. During an earthquake, buildings are subjected to repeated back and forth shaking. This causes of large building displacement and stress release. If a structure is ductile, it can absorb energy and surface. Why ductility is important in earthquake? Earthquake produce dynamic loading. This means force change force change direction continuously. Stress stress reverse multiple times. Large deformation occurs under such conditions. Rigid and brittle structures are is designed. Next is ductile versus rigid behavior. Simple explanation. You can you can explain this with a simple explanation. Imagine bending a plastic ruler and a glass plate. The plastic ruler bends significantly before breaking. That is ductility behavior. The glass plate breaks suddenly with very little deformation. That is brittle behavior. During earthquakes, we went our buildings to behave like plastic, not like glass. How ductility is achieved on RCC structure? Ductility is the reinforcement concrete structure is mainly achieved by proper reinforcement. Detailing concrete concrete alone is brittle. Next slide is about important of importance of structural configuration. Structural configuration means the overall shape, size, geometry, and arrangement of structural elements in buildings. In earthquake engineering, configuration plays a major role in determining how a building will behave during the ground shaking. Why configuration matters? earthquake. When earth occurs, force act in vertical horizontal direction. If the building's shape is simple and regular, forces are distributed evenly. Movement movement is ununiform. Stress construction is minimized. But if the building is shaped irregular, force become unevenly twisted for torsion occurs. Some columns even experience more load than other failures may essentially the weaker add the weaker connection. Next is regular building shapes perform better. Regular buildings are those that have simple rectangular or square plans, uniform mass distributed, uniform stiffness along height, no sudden such as building behave predicted during earthquakes. For example, a rectangular building will move back or back and forth uniformly. There will minimum torsion affected. Regular elevation also matters. Next slide is about base location techniques. Now let us discuss about the most advanced effective earthquake protection techniques. Base location. Base location is a modern seismic protection seismic system that significantly reduce earthquake forces acting on a building. Instead of the building strongly and stiffer, this technique reduces the amount of vibration entering the structure. Basic concept of base location isolation. In a normal building, foundation is regardly concerned to the ground. When the ground shakes, the entire building shakes with it. Full earthquake energy is transferred into the structure. But in the basic isolated buildings, especially devices are placed between the foundation and the superstructure. This device observe and reduce how basic isolation works. This isolation works by increasing the time period of the building. Type of isolation. There are different types of isolation. Lead level, rubber built bearings, LRB. Rubber layers with steel steel plates. Lead core with energy absorption. And high dumping rubber buildings. Rubber absorb vibration energy. Friction pendant system. Sliding mechanism. Reduce force transformation. Next slide is about shear walls. Shear walls is the most important structural element used in the earthquake resistant buildings. Shear walls are play major roles in resistance lateral forces caused by earthquake and winds. What is shear wall? Shear wall is a vertical reinforced concrete wall designed specially, specially to resist lateral loads. Why shear walls are required during an earthquake? Buildings experience strong lateral forces. How shear walls work? Let us understand how shear wall works function. When the lateral loads at the wall behave like a vertical cantilever, it resists bending and shear force. Next slide is about bracing system. Bracing system, which is the another important lateral load resisting system. What is bracing system? A bracing system consists of diagonal steel member provided within a structural plane in a normal rectangular frame made of beam and columns. Why bracing is required? Right? During an earthquake, horizontal forces try to push the buildings sideways without bracing. How bracing works? Bracing mainly works by axial force, tension, and compression. Application of bracing system are commonly used in industrial buildings, warehouses, steel frames buildings, high-rise steel structures. The advantages of bracing system provides increased lateral stiffness, reduced storage draft, store cost of effective solution. The next slide is about rule of foundation in seismic design. Transfer load safely to soil and prevent settlement and tilting. We often focus on beams, columns, and shear walls, but the foundation is quickly important. A strong, a strong superstructure without a proper foundation is unsafe. The foundation is the link between the building and the soil. During an earthquake, this connection becomes extremely critical. Foundation foundation transfer load safely to soil. Under normal condition, the foundation transfer dead load, live load, and wind load. These forces travel through roof to slab to beam to column, and column to foundation, and foundation to soil. Foundation must reset, reset to lateral forces during an earthquake. Foundation must reset with horizontal shear force overturning moment. Means prevent settlement and tilting. Prevent settlement and tiltings. One of the major concerns in seismic design in uneven settlement during earthquake, soil may lose strength, groundwater shaking may causes of compaction, soft soil may behave unpredictable. This can lead to where one slide sinks more than the other causes. Then next slide is building materials for earthquake resistance, reinforced concrete, structural steels, composite materials, reinforced structure, RCC. RCC concrete is mostly common used construction material in India and mainly parts construction concrete is stronger and comparison between weak in tensions. To overcome the weakness of steel, reinforcement bars are added. This combination from reinforced cement concrete RCC. Next is structural steel. Structural steel is one of the best material for earthquake resistance because steel is highly ductile. It is it can undergo large deformation without breaking. Composite construction combines two materials to get benefit of both. Modern earthquake resistant buildings often use compaction composite system to achieve better reference performance. Next slide is about Indian seismic design codes. This is one of the most important aspects of the earthquake materials designs. Designed without following codes is extremely risk and unsafe. In the seismic design is governed by India standards issued by BSI, Bureau of Indian Standard. First one is IS 1893, earthquake resistant design. It is premier code used for critical calculating seismic forces. This code provides seismic force zone classification. Next is IS 13920, ductile detailing. It calculates seismic force correctly using IS 1893. The building may still fail if detailing is poor. This code specifies beam detailing rules, column detailing rules, beam column joint detailing. Third one is IS 4326, earthquake resistant design and construction of buildings. It generally guides construction. This code mainly focus on masonry buildings, low-rise buildings, construction part practice, and seismic bands like plinth band, lat, lintel band, and roof. Next slide is about retrofitting of existing building, existing structure, strengthening old buildings. strengthening old buildings, jacketing and bracing techniques, fiber wrapping methods. It is mainly buildings that exist today were constructed before modern seismic code were impl- implanted. Why roofing is necessary? Roofing, retrofitting is becomes necessary when buildings does not follow seismic codes. Structural cracks are observed. Structure change in use increased load. Next is jacketing techniques. Jacketing techniques. One of the most common retrofitting methods is jacketing. Jacketing means increasing size of strength and size and strength of the structural members. Column and column jacketing and pin jacketing occurs there. The third point is fiber wrapping method. Fiber wrapping methods (FRP). Wrapping is modern roughtering methods. In the tech, in these techniques, fiber sheets are wrapped under columns and beams, epoxy resin bonds, and concrete. Then next slide is about case study of earthquake damage. Example example of past earthquake failure. Less learn from damage. Studying past earthquake failures is extremely important for because seismic design codes are written based on these lessons. Example, the Bhuj earthquake, 2001, one of the most destructive earthquakes in India. Overview of Bhuj earthquake, 2001, 2001, date 26 January 2001, magnitude 1.7, 7.7 magnitude on Richard scale. Location, Gujarat, India. Thousands of buildings collapsed, massive loss loss of life properties. This work causes worse destruction, especially in Bhuj, Ahmedabad, and surrounding regions. Structural failure observed after in, investigation. Engineers identify columns are reason of for a building collapse. Then next slide is about challenge challenges in seismic design. Cost consideration, lack of awareness, skilled manpower requirement. All through earthquake resistant design is technical possible. Implementing it effectively in real world project comes in with structural changes. Understanding these changes is important because engineering is not only about calculation, it is also about practical execution. Cost consideration. One of the biggest challenges is cost cost preparation. Specification. Many people many people will believe that earthquake resistant design will significantly increase construction cost. In reality, seismic design may increase structural cost significantly, typically 5%, 10%, but it prevents catastrophic losses in future. Further, lack of awareness. Another challenge is of lack of awareness among building owners, contractors, local builders, even some engineers in low residential residential buildings. Next point is skilled manpower requirement. Civil design and construction requires skilled professionals. Design earthquake resistant structure involves structural analysis, dynamic load calculation, code code completion, proper detailing. But construction stage is equally critical. The next slide is about further trends in earthquake engineering. Earthquake engineering is con- continuously evolving with technology advancement. We are moving from traditional design approaches to smarter, more recently systems. The first point is about smart monitoring system. Smart monitoring system earlier we used to inspect buildings only after an earthquake, but now we are entering the era of smart structure health health input, health monitoring structure. These systems are sens- sensors, acceleration, and lot of devices, real-time data monitoring. Next point is about advanced management, advanced materials. Traditional materials like concrete and steel are now being improved with advanced technology. Some further materials include high performance concrete (HPS), higher strength ductility, improved crack resistance. Performing this seismic design PBSD design. This is one of the most important advancement. Traditional buildings were designed to prevent collapse. And last point is about conclusion. Earthquake resistant design saves lives. Proper planning and course are essential. Earthquakes are natural phenomena. We cannot prevent them. We cannot stop the ground from shaking.